In this video, I'll be covering some partition identities and we'll be proving them using the generating function. In my last two videos, I have defined what is the partition of an integer and how we can understand its generating function. So just few quick things and then we will start with the partition identity. So partition of an integer, and we denoted the count of the partition of an integer by n. So let me quickly write what do we mean by partition of an integer n. This means that writing n as sum of positive integer such that their sum is equal to n. So we say that this is a particular partition of n. So we can denote that n1, n2 up till so on nk. This is a particular partition. This is a partition of n. And here this is a partition of n, and these ni's, these are called parts or the summand, and these are positive integers, so we can say ni belongs to set of natural numbers. In some cases we may say that partition of 0 is allowed. So in that case, partition of a 0 by convention we consider it as 1 because we are associating this with the generating function, and in that any part may not repeat. So for by convention partition of 0 we will assign it as 1. But otherwise we consider that each part is a positive integer, and in this notation we also consider that order does not matter. Here order does not matter. We can write 1 plus 3 or 3 plus 1, they both are same thing. So just to give an example here, let me to consider n is equal to 5, and here we see that partition of 5 p5, this is 7, and which are the relevant partitions of 5? 5, 4 plus 1, 3 plus 2, 3 plus 1 plus 1, then we can write 2 plus 2 plus 1, and then we can write 2 plus 1 plus 1 plus 1, and 1 plus 1 plus 1 plus 1 plus 1. So you can see that there are 7 partitions of 5. And for more details of the partition, you can please see my previous video, the link added in description. And we have also seen what is the generating function for the partition of integers. So for generating function for Pn, and of course we know that the part sizes, they may come from any positive integer. So part sizes belongs to 1, 2, 3 up till so on, any positive integer. So generating function means Pn x to the power n, n goes from 0 to infinity. I've explained this point in my last video again. So this is 1 over 1 minus x to the power 1 if the part size 1 is coming. Then we can take 1 minus x square if the part size 2 is coming, 1 minus x cube, and so on. So we written this in this form, product I varying from 1 to infinity, 1 over 1 minus x to the power I. This is called the generating function for partitions into any part. Here there are no restriction. Now in this particular video, I want to consider certain partition identities. So let me to start with the first partition identity. The first identity that I'm listing is due to Euler, and it says the number of partition of R into distinct part is equal to the number of partition of R into odd parts. So just to explain this, let me to first again take an example, and then we will look how this identity can be understandable, and we can see its proof using the generating function. So again I am considering same example. Let n is equal to 5. We first write all relevant partitions of 5. These are 7. This is here. Now let me to take it from the condition. It says the number of partition of R into distinct part. So when I say, so these are all relevant partition, and let's just denote it by partition of dn. And here I am considering partitions of n into distinct part, So this subscript d stands for distinct part. We may use any notation such as p, d, comma, n, or capital Dn, the way we want to define. Okay, now we want to count the partition of n into distinct part from above. And for this case, when I take p, d, 5, this corresponding to this, how many are relevant partition? Let's first write them, and then we will see the count. In this case, I've used the notation Pn, that is for the counting of all partitions. So here P5 was 7. This was the count. We have seen there are 7 relevant partition. And now for this case also PD5, I will count how many are these. And let me to first write the relevant partition. Now into distinct part, 5 is already distinct. You can see that there is no repetition. 4 plus 1 is distinct. There is no repetition. 3 plus 2 is distinct. No repetition. Now 3 plus 1 in this 1 is repeating. 2 plus 1 in this 2 is repeating. In the next partition 2, 1 plus 1 plus 1, 1 is repeating. And here also 1 is repeating. So we see that partition of partition of 5 into distinct part is a 3. Now the other side says we want to write the partition of R into odd parts. So let me to just write PON, and here I'm using this is, so these are actually the count of partitions. So let's just write count of partitions of n into odd parts. Now I want to see what is the count and then what will be the corresponding relevant partition. So we are interested in knowing P05, how much is that, and for that we will also look the relevant partition. Now again see from this all partition of 5. Now in this case we want to see which are odd parts. So the first case is again which are relevant partitions. Here the relevant partitions are, of course we will going to take 5 is an odd part. Now 4 is not an odd part, so this particular one will not going to take up in odd. 3 plus 2 in this 2 is not odd. This 3 plus 1 plus 1, this is fine. So we see that 3 plus 1 plus 1, this is relevant because all part sizes are odd. Then this one is also not allowed, this one is also not allowed, this is allowed. So 1 plus 1 plus 1 plus 1 plus 1. This is also another partition of 5 and in which all parts are odd. So we again see how many are they. These are 3, so this is 3. Now we notice that these two are equal. So this is the partition identity. If we are equating two different counts, so then we consider this as a partition identity. So theorem says the number of partition of R into distinct part is always equal to the number of partition of R into odd part. Now the question is how we are going to prove this, and for this I'll be using the generating function for both, and then we'll equate the generating function showing that the count is, because while you expand the generating function it becomes a series and both the series turns out to be the same. So now in the proof we consider again, let PDN denote the number of partition of n into distinct part, and let PON denote the number of partition of n into odd part. So to understand this generating function, now when we are saying into distinct part, so we notice that the part sizes when we write in a partition, so there is no restriction on part sizes except, so first let's understand its value. Part size can be 1, 2, 3 of course, but of course their multiplicity will be 1 or they may not appear because we are saying the parts are distinct. While in odd part sizes we say the size belongs to 1, 3, 5, 7 and so on, because we are considering odd part. So to understand now the generating function, this will be summation PDN x to the power n, n goes from 0 to infinity, this is equal to, now part size 1 is allowed. This I have explained in my generating function. This part 1 may appear in the partition or it may not appear. So if I just consider part 1, it is appearing 0 time, and then we say part 1 appearing 1 time. That's it. We can, if this condition distinct part was not there, then part 1 may appear twice, thrice and so on, and in fact this sequence would go up till infinite. But now since there is a restriction that part size are distinct, so we will have to stop this sequence. Then the part size 2 can come in 0 time and part size 2 can come once. Similarly, the others will follow. So we got the generating function 1 plus x to the power 1, 1 plus x square, 1 plus x cube and so on. And we can write this as product 1 plus x to the power I varying from 1 to infinity. So this becomes the generating function for partition into distinct part. Now for the generating function for partition into odd part, same thing I will repeat with this part size defined according to the odd part. So this will be, now you see the size 1 is coming, and so the part size is odd but it may repeat any number of times. So here part size 1 may come 0 time, part size 1 may come 1 time, part size 1 may come 2 time, and we will continue this one. It may repeat as many as number of time. Then we pick up the another part, that is 3. It may appear 0 time, part 3 may appear 1 time, and we continue. And then for 5, 7 and so on. So we see that this is actually 1 plus x to the power 1 plus x square plus on. This is 1 plus x cube plus x raised to power 6 and so on. And then similarly the other terms. So here we get this first term using the GP will translate into 1 minus x to the power 1. So this is first term. Next term will be 1 over 1 minus x cube. Similarly, the next term will be 1 over 1 minus x to the power 5 and 1 over 1 minus x to the power 7 and so on. Now we want to see, we have looked at the generating functions individually, and now we want to see whether they both are same or not, because we see that we got one from here, one generating function here, and this is my second generating function. If the right hand sides are same, then obviously the left hand side is same. And when the left hand side is same, we say comparing the like powers in this power series, we are going to say PDN is same as PON, and that will prove our identity. So now we consider on one side the generating function for partition into distinct parts. So let me to start with summation PDN x to the power n. N goes from 0 to infinity, and on this has the generating function product I varying from 1 to infinity, 1 plus x to the power I. So now I want to just expand this first. 1 plus x, then we got 1 plus x square, 1 plus x cube and so on, 1 plus x to the power 4 and so on. This is same as if I just multiply, and so if the first term is multiplied by 1 minus x and the divided by 1 minus x. So if I do this multiplication and division to the first term, and similarly I do a multiplication with the second term 1 plus x square, and then I multiply by 1 minus x square and divided by 1 minus x square, and then for the next term 1 plus x cube, and then I take 1 minus x cube and divide by 1 minus x cube, and same process I repeat for every term. So this is same as, now this will become a plus b, a minus b. So this will become a square minus b square. Similarly, a square minus b square can be applied here. And similarly for every term, we can do that. And so this become 1 minus x square over 1 minus x. This is from the first term. The next term will give me 1 minus x to the power 4 over 1 minus x square. The third term will give me 1 minus x 6 over 1 minus x cube. And fourth term, which is due to 1 plus x to the power 4 when I multiply and divide here in this term, will give me 1 minus x to the power 8 over 1 minus x to the power 4. Now and we continue. Now if I just look carefully, 1 minus x square is cancelled with this 1 minus x square. 1 minus x to the power 4 is cancelled with this. And every even term is actually going to cancel with the next terms going to come up in the sequence, in this this product actually. So we are left with 1 minus x, then we are left with 1 minus x cube. These are the terms which are remaining, and every even term is going to cancel from the denominator. It's an infinite series, so we are going to get something like this. And now we notice that every term in the denominator, this is odd, 1, 3, 5, so on. And this is same as the generating function for partition into odd parts. So now if I want to write 1, 3, 5, what I will write? 2i minus 1, I varying from 1 to infinity. And this is same as a generating function for partition into odd parts, x to the power n goes from 0 to infinity. Now we have shown that the generating function of distinct is same as generating function. So their generating functions are different, but if I look at the count while in the expanded form, they are going to give me the same coefficient. And so from here, we can say comparing like powers, comparing these power series, we get PDN. This is same as PON for every n, and this establish a combinatorial identity. Now we consider this theorem, which is another identity. For each n belongs to capital N, the number of partition of n into parts, each of which appear at most twice. So here the condition is that the part size can maximum appear 2 times, is equal to the number of partition of n into parts, the sizes of which are not divisible by 3. So let me to first take an example and then we will move to the proof. Let's consider n is equal to 6 and we know the total partition of 6 is 11. So when I consider P6, this is 11. So now I leave it for the viewers who are watching this to write all relevant partitions for 6 as I've listed for 5. And now on one side I'll write as per the first condition partition of S1 comma n such that this will be the number of partitions of n into parts each of which appears at most twice. So this means the multiplicity of the part will not exceed 2. So that's the first way I've defined S1. So you can say that S1 is actually definitely the same set 1, 2, 3 and so on. Any part can come, but subject to part can come maximum at most 2 times. Okay, so this is appearance. Here this is appearance, not the part value. Now, so this is the first way the function is defined here, and another way that is defined as S2n, this is equal to the number of partitions of n into parts, and in this case part sizes are actually defined. So we say part sizes which are not divisible by 3, So when I say which are not divisible by 3, 3 or 3 is multiple. So here in S2, if I look, 1 will allowed, 2 will be allowed, 3 will not come because 3 will be divisible by 3. So this part will not come. 4 can come, 5 can come, 6 cannot come, 7 can come and so on. So you may write a better way that S2 consists of all k. So we can write it like something all k such that k belongs to natural numbers, but 3 does not divide k. So this way also we can write in the set notation, but here I am just writing in terms of part sizes just to have a more clarity. So in this case PS1 6, we said that we want to write the partition of 6 into parts each of which appearance is at most twice. So the relevant partitions, so we will first count here how many partitions are there and what are the relevant partitions corresponding to this condition. So if I look at the partition of 6, we know that 5 plus 1 is a partition in which the part is appearing at most twice, 5 plus 1. You can also have 6, the first partition. We can have 4 plus 2, you can have 4 plus 1 plus 1. We can have 3 plus 3, 3 plus 2 plus 1, and we can have 2 plus 2 plus 1 plus 1. Now these are the partition in which every part appear at most twice. We can see there is another partition of 6 like 1 repeating 6 times. That's also a partition of 6, but in that 1 is repeating more than 2 times. So only these. And how many are these? If I just count that 1, 2, 3, 4, 5, 6, 7. So there are 7 partitions of 6 which satisfy the given condition. Now similar is, we will count here what are the relevant partitions for this. I want to write the partition of 6 where the parts are not divisible by 3. So it will be 6 will not be allowed because 6 can be 6 is a multiple of 3. So 5 plus 1, then we can have 4 plus 2, we can have 4 plus 1 plus 1, we can have 2 plus 2 plus 2, we can have 2 plus 2 plus 1 plus 1, and then we can have 2 plus 1 plus 1 plus 1 plus 1. And finally we can have 1 plus 1 plus 1 plus 1 plus 1. And so if I just want to see what is the count, PS2 6. Now if just counting 1, 2, 3, 4, 5, 6, 7. This is also 7. So we see that both are equal. So these are equal. And this is what the partition identity says, that whenever we are counting the number of partition of n into parts, each of which appear at most twice, is equal to the number of partition of n into parts such that the sizes of which are not divisible by 3. Now we have seen the equivalence with this example. Let's now prove using the generating functions. So we start considering by the generating function for the number of partition of n into parts each of which appear at most twice. And I said that the part sizes can be any one, 1, 2, 3 on. The only thing is that their multiplicity is restricted. So we start by considering the part size 1. So here the part size can be 1, 2, 3 with multiplicity is less than or equal to 2. So that's how the set is defined. Part 1 coming 0 time, part 1 coming 1 time, and part 1 coming 2 time. That's it. This is the first appearance of the first part 1. Similarly, part 2 can appear 0 time, part 2 may appear 1 time, part 2 may maximum appear 2 time, and we continue this process. Now when we say part 2 coming 0 time or part 1 coming 0 time, we can see this back from the example. Like in this particular partition 5 and 1, here we have not considered part 2, part 3, so their appearance is 0. So this is why we have to consider all relevant cases while creating the generating function. So this point I have explained in my last videos as well. So here it becomes 1 plus x square. The next term will become 1 plus x square plus x4. And the next term which I have not listed here, but this will become 1 plus x cube plus x6. And then it will become 1 plus x4 plus x to the power 8 and continue. Now we will do the similar manipulation as I did in my last identity, Euler's identity. I'll multiply by 1 minus x and I will divide it by 1 minus x. And that's the first term in the previous product, 1 plus x square. So this is the manipulations I am doing. Here again I am multiplying by 1 minus x square and I am doing 1 minus x square here. And so we have the next term 1 plus x. So we are trying to get this into some closed form. And then we do 1 minus x cube, 1 plus x cube plus x to the power 6. And then we got 1 minus x cube. And now then I multiply 1 minus x to the power 4 divided by 1 minus x to the power 4. 1 plus x4 plus x to the power 8. Now we can combine this 1 minus x, 1 plus x square using the identities, and we see that this is 1 minus x cube over 1 minus x. So that's how the first term reduces. First term converts, not reduce. So this will become 1 minus x to the power 6, 1 minus x square. The next term will become 1 minus x to the power 9. So if you just multiply, we get, you can see that this is x cube and here it is x6. So we get a nicer formula 1 minus x to the power 9. This is 1 minus x cube. And this one will be 8 and 4. This one will be 12. 1 minus x to the power 12. 1 minus x 4. Other terms get cancelled and so on. So this is how the sequence will go on. Now in this also we notice very carefully that in the numerator, we are only getting a multiples of 3. And they are also appearing in the denominator, like 1 minus x cube is appearing here. Similarly, 1 minus x to the power 6 will appear in the next term and so on. So when and this is an infinite product. So the numerator gets cancelled with this denominator. 1 minus x to the power 6 will cancel with the terms appearing here. And 1 minus x to the power 9 will cancel with the terms appearing here in this infinite product. So we are left with the terms only 1 minus x square, and we see that 1 minus x cube is missing. The next term is 1 minus x to the power 4. Then the next term will be 1 minus x to the power 5. So 1 minus x cube is again cancelled. So the next term is 1 minus x to the power 7, 1 minus x to the power 8, 1 minus x to the power 9 will be missing. So the next term will be 1 minus x to the power 10 and continue. So this is the same as product 1 over 1 minus x to the power k, and this k belongs to natural number such that 3 does not divide k. So that's how we leave this term. So here k varying from 1 to infinity you may write, or we have already written k here. So this is a product, and so now we have seen this is same as the generating function that we require. So this is p s2n x to the power n goes from 0 to infinity, and so from here we can always write that p s1n, this is equal to p s2n for every n, and this proves our identity. Now the last theorem was generalized by Glaisher in 1883, and the statement was for any n and k, small n and k belongs to capital N, that is a set of natural numbers, the number of partition of n into parts, each of which appearance is at most k times, is equal to the number of partition of n into parts, the size of which are not divisible by k plus 1. So in my last example we have seen we have restricted the multiplicity to 2. The parts cannot repeat more than twice. So the number will not be divisible. The next on other side, we said that the parts will not be divisible by 3. So that's a simple extension of that. So we look at the proof of this one, which is an extension of the previous case only. And here we will start the generating function for the number of partitions of n into parts, each of which appears at most k times. So that means the parts multiplicity is fixed. And so this will be simply 1 plus x. So this is the first part, size 1, and it is appearing at most k times. So we can see that this is k times. Up till k it will restrict. So this was like x to the power 1 appearing 0 time, x to the power 1 appearing 1 time, and x to the power 1 appearing k time. That's it. We cannot take it as infinite because the appearance is at most k time. So this is how I have written the first case. And now let me to write the second case. The part 2, then x to the power 4, and then the part 2 can come k times. So this means the last term will be x to the power 2k. Similarly is the part size 3, and this can come in k times. So x to the power 3k. And this way the term will go on. Now this is again, I'm going to multiply the same thing. 1 minus x you multiply, and then we divide 1 minus x, the same first term, x to the power 1 x square plus 1 plus x to the power k. Now the similar multiplication in the next factors, x square and then 1 minus x square here, we get 1 plus x square plus 1 plus x to the power 2k. And similarly here 1 minus x cube, and then in denominator we get 1 minus x cube, 1 plus x cube plus on up till x to the power 3k, and we continue the similar multiplication in the remaining one. Now from here we can see that if I just multiply these two terms, we will get 1 minus x to the power k plus 1. So you can just notice that here other term get cancelled. This is x to the power 1, and then when it is multiplied with the last term, it is x to the power k plus 1. The remaining terms are going to cancel out. You can see after the multiplication. So this step I leave. When you multiply the 1 minus x with the next term, or you can simply apply the identity formulas. And so here it is 1 minus x. So that is from the first term. Now the next term will give me 1 minus x square, and in the numerator I get 1 minus x to the power 2k plus 2. So just add the last two, other terms get cancelled. The next term give me 1 minus x to the power 3k plus 3. And then we got 1 minus x cube and so on. Now if you look at carefully, in the numerator we only have a multiple of k plus 1. So the first term is k plus 1, next term is twice of k plus 1, and the next term is 1 minus x to the power thrice of k plus 1, and similarly the next term will be like this one. And in the denominator we have all terms, 1 minus x, 1 minus x square, 1 minus x cube, and we continue all the term. Now this is an infinite product, so at some stage we are definitely going to get 1 minus x to the power k plus 1. We are definitely going to get 1 minus x to the power twice of k plus 1. This is going to come up in this product. And when they come up, this 1 minus x to the power k plus 1 is going to cancel with this one, this is going to cancel with this one, and this is going to cancel with the next term that is going to come up. So from here we see that we are left with the sequence only in which the k plus 1's multiples are not coming. So this will be something similar. We can write 1 over 1 minus x to the power j, such that j belongs to set of natural numbers, such that k plus 1 does not divide j. So that means all the terms of j which is not a multiple of k plus 1, they will be coming up. And here j varying from 1 to infinity. So when I say 1 to infinity, that means accepting these terms, or you can write the condition here, or we can write product j varying from 1 to infinity such that k plus 1, this is not a multiple of j. So this equals to the generating function for number of partitions of n in two parts where the part sizes are not divisible by k plus 1. And that proves the another partition identity. And in my next video, I'll be taking some partition identities using the Ferrer's graph. Ferrer's diagram is the graphical representation of a partition.